two matrices A and B, we can multiply these matrices A times B This is important. We can multiply them in this exact order. We're not talking about B times A. We're talking about A times B in this exact order. In other words, this is not like multiplying numbers, where multiplying 2 times 3 is the same thing as multiplying 3 times 2. This is not like that. The order in which you multiply matrices is very important. So we're talking about A times B only if we can multiply them in this order. Only if Okay, this is such an important definition or description. We can only multiply A times B only if the number of columns in A, the first matrix, is equal to the number of rows in B, which is the second matrix. So let's see how that works. So I'm going to say the same thing using symbolically. So let me say, in other words, A times B. Suppose A has dimension m times r. Then B has to be has to have dimensions r times n. Notice the reason for that is that the number of columns in A must always be equal to the number of rows in B, the second matrix, if we are to multiply them in the same order. So we say r equals r. Therefore, multiplication is possible. Okay. Having said that, the question is, what is going to be the dimension of the resultant matrix? Okay, the dimension of the resultant matrix always comes from the other two numbers in the dimension. So that one and that one will give us m times n. And this is the That's going to be the dimension of the resultant matrix. So when you write down the dimensions of each matrix, make sure that the first matrix has equal number of columns as the rows in the second matrix. That means the multiplication can be performed. And then you have to know what is going to be the dimension of the resultant matrix, in which case you look at the other numbers. The rows of A and the columns of B give you m times n is going to be the dimension of the resultant matrix. In other words, the number of rows of the resultant matrix are going to match the number of rows of the first matrix here. The number of columns of the resultant matrix are going to match the number of columns of the second matrix here. Okay, and that's also That's the same thing we said up here, but more in symbolic form. Okay, so let's talk about an important note at this juncture. If A times B in this order, if this is possible, and let me underline does not mean. Very, very important. So if you multiply two matrices in one order, and that's possible, it does not mean that if you change the order B times A, that's also possible. Okay, one does not mean the other one. So, in fact, I'm just going to continue on that. In fact, so given the two matrices we just talked about in the previous page, so let me write them again. A times B. A had dimensions m times r, and B had dimensions r times n. In this case, B times A is not possible, right? Using that same example, this is not going. B times A is not going to be possible. Why? Let's it's not possible, and let's say because here's why. Right? If we switch things around, if we say B times A, we know that B has this dimension, r times n, and A has this dimension, n times r, and compare these two together. In order for this to be possible, n has to be equal to m. In other words, they have to be the same letter, right? Which was the case in the case of A times B. But n, because it's a different letter, so that means n and m are not equal. So multiplication is not possible. Okay, this is all checks we have to perform before we multiply two matrices. Okay. To this rule that we talked about, this rule of matrices, the order of matrices matter when we multiply matrices. To this rule, there is an exception. Let's see what that exception is. Well, let me say it this way. So exception, in parentheses, I'm going to say the identity matrix. First, before we talk about the exception, let's see what an identity matrix is. So, the identity matrix of size 2 by 2 is is this matrix. That's an identity matrix. For any 2 by 2 matrix has this as its identity matrix. Let's give the other identity matrix. So the identity of size 3 by 3 is like this. Like that. So when you multiply any matrix by its identity matrix, it's exactly as if you're multiplying a number by 1. So 5 times 1 is 5, right? So the same thing goes with an identity matrix. You multiply any matrix by the identity matrix, you get the original matrix back. Just like 3 times 1 is 3, negative 2 times 1 is negative 2. Any matrix multiplied by the identity matrix is equal to the original matrix. So before we show that, so this is, so basically what we're saying is, so this is what we're saying. So we're saying that A times the, let me call this identity matrix, I for identity matrix. So A times the identity matrix for it, whatever the size of this is, the size of the identity matrix will be exactly the same size. So if A is a 4 by 4 matrix, the size of the identity matrix is also 4 by 4 matrix. And it's going to look like this. That would be equal to I times A. Notice I changed the order. In both cases, the result is equal to the original matrix. So this is the only exception we have for the order of 2 matrices that are being multiplied by each other matter. In this case, it doesn't. When you multiply a matrix by its identity matrix, you can multiply them in any order. It doesn't matter. You get the same thing, which is the original matrix. Okay, so we've talked about all these definitions and descriptions. So now let's actually go through a few examples. So suppose we want to multiply these 2 matrices. We have 1, 4, negative 1, 2, 2, 0, 6, negative 1, 4, and 1. Okay, so first let's check quickly what the dimensions are and if this is possible or not. Well, the dimensions of this one is 2 by 2. Dimensions of this one is 2 by 3. And the number of columns in the first one is equal to the number of rows in the second. 2 equals 2. So yes, the multiplication can be performed. And the next question is, what is going to be the size of the resultant matrix? Well, that is given to us by these 2 numbers. So 2 by 3. So that's the resultant matrix. Or the size or dimension of the resultant matrix. Okay, so we know that's what we're going to get. All right. So how do we then perform this operation? Let me write it here. I'm going to duplicate this here. like that. Okay, so the way this method works is like this. To multiply two matrices, we take the first row of the first matrix, multiply it by the first numbers in the first column of the second matrix, and add them together. So how would that be? Well, let's do it step by step. So we will do 1 times 2 plus 4 times negative 1. And we know this what kind of a size we're going to get, right? We're going to get the 2 by 3 matrix. So that and if you're wondering what I'm doing here, this is the conventional matrix notation. This is saying that this number is in row 1, column 1. That's why A11. A12 means this number is in row 1, column 2. A13 means this number is in row 1, column 3. So this number is in row 2, column 1, row 2, column 2, row 2, column 3. It's just giving the position of that number within the matrix. Okay, so then once we do that, you do the same thing with the second column. You multiply the first row by the second column. So you get 1 times 0, and then add the results, right? 1 times 0 plus 4 times 4. We're done with that. Then you move to the third column. You multiply the first row by the third column. So we have 1 times 6 plus 4 times 1. Like that. Once we've run out of the columns in the second matrix, then we switch rows. We switch to the second row, and we repeat the same thing. We multiply this by the first column and write it here. Then we multiply it by the second column and then the third column and write it here. Okay, so let's do that. So negative 1 times 2, right? Take the first row, multiply it by the first column. Add the numbers, then multiply the second row by the second column. Second row by the third column until we run out of columns. So we're going to have negative 1 times 2 plus 2 times negative 1. Negative 1 times 0 plus 2 times 4. Finally, negative 1 times 6 plus 2 times 1. Okay, so now we can simply do the arithmetic on this and find the resultant matrix. So we have 2 minus 4, that's minus 2. And then we have 0 plus 4, that's 16. Then we have 6 plus 4, that's 10. We have negative 2, minus 2. Minus 2 plus minus 2, that's minus 4. We have 0, right? 0 times minus 1 is 0. Plus 2 times 4, that's 8. Minus 6 plus 2, that's minus 4. And we have the final result. So that's one way of finding or remembering what to do to find the product of two matrices. That's one way. Is there another way? Yes, and I'm not sure if you prefer this over the first method, but I'll talk about it, and then I'll leave it up to you how to remember the method for multiplying two matrices. So another method of remembering what to do is once you figure out the size of the resultant matrix, which in this case was 2 by 3. So, and I wrote it above. I'm going to duplicate it here. here. So these subscripts are very, very important because not only they tell the position of that number, any of these numbers or elements within this matrix, so row 1, column 2, row 2, column 1, row 1, column 1, row 1, column 3, and so on. Not only they give us the position, but also when you multiplying matrices, they tell you how you can get this number. So this is saying multiply the first row of the first matrix by the first column of the second matrix. So that's another interpretation of these subscripts. Multiply the first row of the first matrix by the second column in the second matrix. Multiply the first row in the first matrix by the third column in the second matrix. Multiply the second row in the first matrix by the first column in the second matrix. 2, 2 would be interpreted as multiply the second row in the first matrix by the second column in the second matrix. Multiply the second row in the first matrix by the third column in the second matrix. Okay, so that's an interpretation of that. Okay, let's see another example. Suppose we want to multiply these two matrices. Once again, let's run a check if this can be performed. Here, the dimension of this one is 3 by 2. The dimension of this matrix is 2 by 2. The number of columns in the first one is equal to the number of rows in the second. So yes, we can perform the multiplication. The question now is, what is going to be the size of the resultant, the product matrix? Well, that number comes from the other two digits. So it's going to be 3 by 2. So let's see what would that look like, or how would that look? It would look as this. So 3 by 2 would be 3 rows, so A11, A1, and only 2 columns. So A11, A12, A21, A22, A31, A32, right? So this is saying that row 1, this number is in position row 1, column 1. This number is in position row 1, column 2. This is in row 2, column 1. This number is in row 2, column 2. This number is in row 3, column 1. This number is in row 3, column 2. And then how would we get each number? For example, this one. How would we get this number? Another interpretation of this subscript number is this. You can get this number by multiplying the third row in the first matrix by the second column in the second matrix. Okay. So now let's, can it be, well, let me write it because it's going to be off the screen. I'm going to duplicate the same thing I wrote above here so you can look at it as we go through the operation. I'm just duplicating what was up there. Like that. Okay. So we know that the matrix, the resultant matrix is going to look like this. 3 rows and 2 columns. So let's do that. Let's get that matrix. So start with the first row, multiply it by the first column, add the numbers, then multiply the first row by the second column. When you run out of columns, switch to the second row and repeat the same thing. So 2 times 2 plus 0 times 3. right? We're doing this. This row multiplied by that. 0 times 3. Now once we're done with that, we move to multiply the first row by the second column. By that one. So we say 2 times 1 plus 0 times negative 2. We've run out of columns, right, to multiply it by the first row. So we switch to second row and repeat the same thing, column by column. So we say 4 times 2 plus negative 2 times 3, right? Then the second column, 4 times 1 plus negative 2 times negative 2, right? We ran out of columns. So what do? We switch to the last row, that one, and we multiply column by column. So 6 times 2 plus negative 1 times 3. Then the second column, right? 6 times 1 plus negative 1 times negative 2. Like that. Okay, so now we do the arithmetic part. 4 plus 0 is 4. And 2 plus 0 is 2. 8 minus 6 is positive 2. 4 plus positive 4, because negative 2 times negative 2 is positive 4, plus 4 is 8. 6 times 2 is 12, minus 3, that's 9. 6 plus 2, because negative 1 times negative 2 is positive 2, plus 6, we get 8. Okay, so here we have the result of that operation. Okay, so let's do another example. Suppose we want to multiply these two matrices, and after this we'll do one example with multiplying two 3 by 3 matrices. Okay, like that. Well, the dimension of this matrix is 2 by 2. This is 2 by 2. The number of columns in the first matrix is equal to the number of rows in the second one, and the resultant matrix would be 2 by 2 as well, right? Because that and that would be 2 by 2. Okay, so we do the same thing. At any point, feel free, and I encourage you to pause the video, go through the multiplication on your own, and then look at my solution. So here we have this first row, first multiply it by the first column, then multiply it by the second column, right? So 2 times 2 plus 0 times 3, we're done with the first column. Then 2 times 1 plus 0 times minus 2. Then 4 times, this, we're out of columns, right? So we switch to the next row in the first matrix. So 4 and negative 2. Okay, so 4 times 2 plus negative 2 times 3. That column is done. Let's move to the second column. 4 times 1 plus negative 2 times negative 2. right? So let's do the arithmetic for this. 2 times 2 is 4, plus 0 is 4. 2 times 1 is 2, plus 0 is 2. 4 times 2 is 8, minus 6 is 2. 4 times 1 is 4, plus positive 4, because negative 2 times negative 2 is positive 4. We get 8. And here is that result. Okay, so having done that, let's multiply a 3 by 3 matrix by another 3 by 3 matrix. So we have, I guess, I better do that on the next page because I don't think I'll be able to fit it on this page. So we want to multiply these two matrices. Okay, both of these are square matrices. With square matrices, you can always multiply them. But remember, the order is still important because if you multiply this matrix by that, you know you're going to get a 3 by 3 matrix, another square matrix of the same size. But that matrix is not going to be equal to if you switch the order of multiplication. If you put this matrix first and this one second, you're able to get another 3 by 3 matrix as the result, but that matrix is not going to be equal to the same result that you get from this order of multiplying these two matrices. Just remember that. Okay, so this is the same way. I'm just going to, I don't want to clutter the page, so I'm going to remind you that what we'll do is take the first row, multiplied by the first column, add all those numbers, then multiply this first row by the second column, add those numbers, and then multiply that by the third column and add those numbers. So, and the resultant matrix is going to be a 3 by 3 matrix. So we already know where we're headed. Once you run out of columns multiplying the first row, then you switch rows. You move to the next row and you repeat multiplying by each column and adding those numbers. When you run out of columns again, then you switch to the bottom row and repeat again. Okay, so let's do that. I'll try to fit this on the screen. Like that. I think that barely fits. Okay, so first row multiplied by the first column. We have 3 times 2 plus 1 times 3 plus 0 times 1, right? That's the multiplying this by the first column. Let's move to the second column. This by the second column. So we have 3 times 0, right? 3 times 0 plus 1 times 4 plus 0 times 6. Then the third column, 3 times negative 1 plus 1 times negative 3 plus 0 times negative 2, right? It barely fit. Okay. Then we're out of columns, so let's move to the second row. Negative 2 times 2 plus 1 times 3 plus 5 times 1. Then the second column. Negative 2 times 0 plus 1 times 4 plus 5 times 6. All right? Then the third column. This row, second row, multiplied by the third column. So negative 2 times negative 1. 1 times negative 3. 5 times negative 2. We're out of columns, so we're going to switch to the bottom row. So this row multiplied by each column, right? Let's do that here. 4 times 2 plus 3 times 3 plus 2 times 1. Then the second column, 4 times 0, 3 times 4, 2 times 6. And now the third and last column, 4 times negative 1, 3 times negative 3, and 2 times negative 2, like that. Okay, so now all we have to do is do the arithmetic. So here we have 6 plus 3, 9 plus 0 is just 9. Here we have 0 plus 4 is 4, plus 0 is 4 again. Here we have negative 3 plus another negative 3, that's negative 6, plus 0 is negative 6. Here we have negative 4 plus 3, that's negative 1, plus 5, that's 4. Here we have 0 plus 4 is 4. We have 5 times 6, 30. 30 plus 4 is 34. Over here we have 2, positive 2, right? Negative 2 times negative 1 is positive 2. Plus negative 3, that's negative 1. Plus negative 10, that's negative 11. Okay, we're working our way through all this arithmetic, basic math. So 8 plus 9, that's 17, plus 2, that's 19. That's 0 plus 3 times 4 is 12. That's 12 plus 0 is 12. Plus another 12 from these two, we get 24. Finally, we have negative 4 minus 9. That's negative 13. Minus 4 and minus 13, it's minus 17. Okay, so let's clean this up and write it nicely. The final result is 9, 4, negative 6, 4, 34, negative 11, 19, 24, and negative 17. I'll move this up like this. Like that. Okay, I hope this section helped you fully understand how we multiply matrices. And with having said that, we finished section 3.2, and I look forward to have you with these series of videos next time when we will talk about section 3.3, which is about finding the inverse of a matrix. For now, have a nice day and stay safe.